The random walk on a clock was proposed by the 3 Blue 1 Brown channel, and I loved it because it looks like a simple random walk and the result turns out to be surprisingly unintuitive. I leave the link below. Here's the setup. A ladybug starts at 12 o'clock, and at each step we flip a fair coin. Head moves 1 hour clockwise, tails move 1 hour counterclockwise, and the clock wraps around forever. We keep walking until every hour has been visited at least once. So, which hour was visited last? If you're thinking 6 o'clock should be last more often because it's far away, well, that is the trap. Because the actual result is every non-starting hour is equally likely to be the last new hour. On a 12-hour clock, each hour from 1 to 11 has probability 1 over 11, which is about 9.09%. The way I solved it was, first I verified it with a simulation, then I modeled the process as a state graph, and finally the answer becomes inevitable, because the state graph has a one-way downward structure plus symmetry. I started by simulating huge numbers of walks on the 12-hour clock, and the last visited frequencies came out essentially identical for every hour. It's a clean empirical signal, and the probabilities really are equal. The key move is, we don't describe the system by position alone. We describe it by a state, meaning current position plus the set of visited hours. So if I walk away from 12 and later come back to 12, I am not back where I started in the state graph, because the visited set has grown. The history matters, and that's exactly what the last visited question is about. This is why I like to start with a tiny clock, like 3 hours, because you can see the shape of the state space. Every time the ladybug discovers a new hour, the visited set gets bigger, and that's what creates a notion of levels. Once you see the levels, termination becomes obvious. You can wander sideways for a while, but on a finite clock, you can't do that forever without eventually stepping into something new, and each new discovery drops you one level closer to the bottom. Now, in this state space, the process is literally a Markov chain. From the current state, the distribution of the next state depends only on where you are, which hours are already in the visited set, and the fair coin flip. It doesn't depend on any earlier history beyond that. At the bottom are the states where all hours have been visited. And the moment you first reach that bottom layer, your current position is exactly the last newly visited hour, because you had to step into the final missing hour to complete the set. So if we stop right there, meaning that once we reach the bottom we just stay there, then which hour is last becomes a clean Markov chain question. Is the probability of ending in each final state, starting from the initial state at the top. Now the punchline. Because each step is a fair coin flip, the walk has no directional bias, and because the clock is symmetric, the state graph has no built-in preference for any particular non-starting hour to be the final one. In other words, if hour k had a higher chance of being last than hour j, that advantage would have to come from somewhere in the rules, and there is nowhere for it to come from. So the only consistent answer is that all non-starting hours share the probability equally. There are n-1 non-starting hours, so each has probability 1 over n-1. For n equals 12, that's 1 over 11. And this is exactly what the 3D animation makes intuitive. As the ladybug runs, the graph below is full of possibilities, but the graph above becomes unreachable because you can't unvisit an hour. It's literally a process where most motion is downward, sideways wandering is allowed, upward motion is forbidden, and the terminal families at the bottom end up receiving equal total probability. So that's my solution in a nutshell. I confirmed the phenomenon by simulation, modeled the process with a state graph where states are position plus visited set, and then the equal probability result becomes inevitable because the graph is one-way top to bottom flow with perfect symmetry. And that's why, on a 12-hour clock, 6 o'clock is last with probability 1/11, exactly the same as every other non-starting hour. If your intuition still protests, here's the reconciliation. Far hours do have more ways to end up last, but those ways usually require longer wandering, and longer wandering costs probability step by step, so the two effects cancel perfectly.